Okay, hello and welcome. This is a Power World tutorial, and we're looking at a specific example today from the Glover textbook, and I'll show you what each symbol means in this and how to simulate this particular primary loop distribution system. So first and foremost, a little background on this particular primary distribution system. It is interesting to note that a loop system is not the most commonly seen because it's not the most cost effective and low cost option. In low density demand areas, such as very rural areas, you will see a radial system. However, this is more reliable because you can sectionalize faults and isolate them so that they can be serviced and repaired. So a few characteristics of a primary loop system is that they're very compatible with automation, and now that there is more monitoring and control thanks to the Internet of Things and low cost of computers, we're able to automate these systems more and isolate faults and sectionalize them. A loop system is pretty easy to imagine. Here's the basic elements of it. You can see that from the transmission bus we go down to the distribution level, and then this loops around and it returns to the transmission bus, so you really have two ways of power flowing. And this circuit breaker is intentionally left open under normal operations. So the loop will contain reclosers and tie switches, sectionalizers, and circuit breakers used to isolate faults, and reclosers will automatically open and close in order to clear faults, which keeps the customer online longer. And when building these systems, the cable that's used for the loop will be of sufficient diameter to accommodate the entire loop, so that if one of these goes out, this can be opened and the rest of the customers will be able to be, their demands will be able to be met. So without further ado, I'll show you what just happened and give you kind of a rundown of this diagram. So starting at the top, we have the transmission bus, and we can select the taps here. Everything is in per unit values, and per unit notation is very helpful because as you change the voltages, the per unit changes with it. So for example, 1 per unit voltage, in this case the base voltage could be 138 kilovolt rating, so 1 would be equivalent to this if that's your base value. So it's very easy to visually look at something like this and not have, this way you can go down the line as you're passing over transformers, and as the voltages change over the transformer, the per unit will change as well because you're changing the base value. So if that was too confusing, basically what you're looking for when you trace back up to high voltage is that everything will be 1 per base value. The per units will change, so it makes it very, you're dealing with easier numbers than say 138 to 13.8 kilovolts to 120 volts. It makes it very, it makes the math a little bit more convoluted when you do stuff like that. So we're delivering load. Each of these is a customer. Here we have commercial, and we have different commercial, residential, and industrial customers. You'll notice a lot of the commercial and industrial will be drawing and demanding reactive power in addition to real power. Real power is in megawatts, and reactive power is in megabars in this case. That always applies, but reactive power, also known as imaginary power, also known as quadrature, that is delivered to the customer for use of AC motors such as elevator lifts. They require reactive power for normal operation. So what we're doing, just to give you a rundown of this diagram, is we're starting from a higher voltage and moving high voltage, low current. Then we step down to the distribution level at a substation, 13.8 kilovolts, which is standard distribution. It's most common in the United States. It's a safe distribution level to deal with, and it's most common amongst modern distribution systems. Older distribution systems are within the 5 kilovolt class. Some are around 4 kilovolts for the older systems, but we're using more electricity now, and the population is more dense and there's more of a demand. So 13.8 kilovolts runs out through the system. These pie charts give you an idea of the current that is being drawn, as well as the megavolt amps, which is your total power. And we're tapping. We have a function to tap into this 138 kilovolt transformer. So a tap is basically you're tapping up or tapping down. They're physically switches, and it's moving the conductor within the transformer to select how much voltage you're drawing out of that transformer. So this is basically, in a nutshell, this is like playing SimCity, and you can change one little thing and see how it affects everything else. And it's a very helpful simulation tool because mathematically it would take you a very long time to do this, and it's very complex and convoluted. But in a system like this, it's all out in front of you, so you can simulate and see what would happen. So the example in the book involves a sectionalized fault and isolation of 9 commercial. So we're going to open these circuit breakers here, and then we realize that we now have 0 per unit voltage going to all these locations, and there is no power being drawn. The end here is the load of the customer. So what we have to do is open this, and we're going to let this transformer take over. So I open here, and we can see that we're drawing an incredible amount of current here, but it's actually not. It'll get orange and then red if we draw too much. And then in the case that it's red and you fill up this entire circle, you've drawn too much current, and you're going to have a blackout because this wire will fry, or a transformer or a substation will blow up, and that's something that you definitely don't want to happen. So we can see here that we are able to supply the entire loop up to the sectionalized fault with power. Even this last 10 residential is receiving 1 megawatt of power, so their needs are met. Really quick, these are shunt capacitors, which help with the efficiency as well as supplying the reactive power. They compensate for the reactive power that's being delivered. So it's hard to see in this diagram. There's a rule about where to place these, but that's something that this is just a given within this program. So we see that when we open 9, so this is normal operating procedure, our case losses for this entire system is 0.16 megawatts, or 161 kilowatts. And so we can run it like this, but our losses are increased. So we have an increased I squared R loss due to the fact that the lower voltage, higher current of the distribution line has to travel further to reach these loads. So it's a matter of fact that you're going to get more I squared R losses the further distance that you have to travel. So the loop system works well, and it's more robust than a radial system in most cases because you have the dependency upon another line from the transmission bus and the distribution that's going to cover this area. And these are built with future considerations in mind based upon demands. And there are other things that you can look at within Power World to try to get this case losses to the lowest possible value. For instance, if you happen to remove some of these shunt capacitors, well, that removes the load, but if you remove a shunt capacitor here and here, I notice that it lowers the losses. And sometimes this is a bit of an art, trying to balance out what you're going to turn on and off, but you can see the implications of how distribution automation is very practical and the way of the future. Thank you for watching my video.